All right, so before we get started, so the original midterm date was next Monday, but I got several emails saying this conflicts with another midterm that apparently goes on for many days at this point. So if you're taking that class, can you tell me a little bit more information about that midterm? I got several emails, but I was a little bit confused on how the other class is working. I'm guessing if you're taking that class, you would know. I don't know. So I got several emails saying there are some class that's a conflict with this midterm because yeah, so can folks give me more information about that one? So we can reschedule our midterm if needed, but I'm slightly confused about what exactly the conflict is.
I think the class is 452.
Okay.
And basically the midterm is released on Thursday night. And then it's due on, I think, Monday night, although someone else in 452 can correct me if I'm wrong with that. And it's just it's a take-home midterm with a lot of time, but it's supposed to be super hard.
That's supposed to be hard. Okay.
I mean, that's what he says. So that's basically the gist of it.
So this is the power electronics class for 52?
Yeah.
Yeah, okay. How many of you are taking that class? Because if you are saying chat, I'll take a look. So if there's a lot of people, then it's probably easier to delay our midterm. It's 1 or 2 can work out special. All right, okay. Okay, so there's a good number of you taking that class. So let's not conflict with 452. So was it supposed to be earlier, or did they change the date?
Yeah, he originally had it scheduled for today, at least on the syllabus and everything, and then he decided to have it.
Wait, when did he say it was changed?
It didn't change. It changed from what he originally posted in the syllabus.
It was supposed to be today, right? And do online.
Yes, but now it's starts Thursday night.
Yeah, so I got several emails about this, so I was also confused on the exact timing. But it looks like there is enough people conflicting with this, and given if we have it on Monday, you'll be basically the morning will be this exam, then there may be some conflicts with the other ones. It's due Monday night. So the easiest thing for us is probably to push it to next Wednesday, right? Next Wednesday morning. Right, so we can't move it, right? So we can't move it ahead of time. So we push it, then probably we'll need to push it to Wednesday. Right, so I understand, so it's a 4-day exam, but when people give you 4-day exams, means the exam will take you some time. So in school, I had a 1-week take-home exam. The entire class solved half a question on that midterm. So I understand this sort of 4-day take-home exam can take a long time. So if we push it to Wednesday next week, right, we can push it to Wednesday. Anybody have a conflict with that? Anybody have conflict Wednesday? What day is Wednesday next week? So the 10th. Sorry, not the 10th. The 11th. Oh wait, is the 11th a holiday?
The 11th is Veterans Day, but not the observed day for Veterans Day. I actually think, I don't know which day is the observed day for Veterans Day. I think it's we might be doing it, I don't know which day it is, but usually we have a Monday off near Veterans Day, but that's what the holiday is.
Okay, so let's check whether that's a holiday or not. If not a holiday, we'll do it that day. If it's a holiday, I guess we'll figure out. Academic calendar, holidays. Yeah, there's no class on that day, Veterans Day. Class not in session. So we can't do it on a holiday, right? Veterans Day. So we can push it. So what I can do is I can also make it a take-home one. I can release it on say Wednesday morning and collect it by say Thursday night. Does that work? Or should we just push it one more week and have on the Monday after?
I like the idea of the take home because that is flexible with people that are in different time zones too.
All right, so anybody against the take home? It wouldn't be that much harder. We'll just do it as take home. Like it's not gonna be twice as long, but just we can't do it on Wednesday, so I may just well release on Wednesday morning. Anybody against take home? Anybody says no to take home?
Absolutely no problem with that.
Okay, all right. So the plan right now is we'll push it. So it's not gonna be Monday next week, right? Because of conflict. Wednesday will not be during class time because it's a holiday. So the midterm, I guess I'll release it Wednesday morning. Then I'll collect it Thursday midnight, right? So 11:59 p.m. Thursday. And the midterm will be, I guess, slightly longer because it's take home, but difficulty-wise will be similar level. Are we okay with that? Are we good? Any other conflicts?
Yes, this is good. Thanks for making accommodations for our other class.
Okay, so let's do it that way then. Okay, so I'll make a formal announcement and I'll change the website and syllabus after this class. But for now, we'll do it take home Wednesday morning to Thursday evening, right? Okay, so that's I understand. So some people may have other sort of special considerations, but if you need that, let me know. Right? If there's no systematic conflict, then we'll go with this time for most of the class. Okay, so that's fine. So I guess in terms of the material covered on the midterm, then we'll cover to, let's see where we get to today. We'll decide, where exactly the midterm covers. Let's see where we get to today. Right. So I'll take home, doesn't change any logistics of the midterm. Right. Still, you can use technology, you can Google, you can use computers, whatever you want. Again, no communication, right, with each other. So, and this midterm would not be, you won't have open-ended questions. So it'll be like similar to homework. There's a problem, solve for something, current, voltage, power, and write down steps. Okay. Right. So okay. So let's go with that. So the midterm again is Wednesday morning next week. I'll release it at 11:59 p.m. Thursday night. I'll collect it. Okay. So we'll do it that way. Right. So any other issues, I guess, since we're on this topic about the homeworks, the midterms, anything else, feedback about the class you want to discuss before we start?
So the midterm is next week.
Yeah, the midterm is next week. So midterm is, so right now the timing is next Wednesday morning. I will post it. You hand it back in Thursday, 11:59 p.m.
Thank you.
Yeah. Okay, yeah, so thanks. Yeah, so yeah, again, in the future, any conflict like this, please let me know, right? We can, virtual does making this kind of changes easier, I'll say, right? So if you have other conflicts, let me know. For final, it'll be a little bit harder. So for final, we can still change dates, but it's considerably more difficult. So if similar issue come up for finals, do let me know early, right? We can still do it, but finals are, since we're tied to the academic calendar, will be a little bit more difficult if a final conflict. But still, we can make different arrangement. Okay. And for those who email me about individual considerations, I'll follow up with that. Right. So this still, if you, for example, someone has jury duty, you have that, then we'll work out time differently from that. All right. So continue with last week recap. So what we did last week is basically we said if we have a large power system, basically we have many buses, right? So some network connect to some loads. Right, so let's think of this as the Y matrix. Okay, so from now on, when we describe a power network, we will give this Y emittance matrix. Okay, so this we're going to think a power system is described by this matrix. Because this matrix encodes both the topology of the network and the parameters inside the network. Okay, so this has topology and parameters. Okay, so so this is the 0, 1, right? The 0 non-zero pattern tells us which lines connect which line, and then the values on the off-diagonal terms tell us the admittance between the two buses. Okay. So again, why, right? So if you look at the individual line, so far for most of the classes we have, for power system or circuit analysis classes, we look at the impedance of the line. For a single line, the impedance is a little bit more intuitive value to understand. But if we have a large system, we want things to add when things are collecting parallel. So that's why 1 over Z, the admittance, is used very much more often for large scale power system. Okay, so again, for example, if you read academic paper or you read a sort of high level textbook, you almost never see impedance. You will never see impedance. Everything is in this term of this Y matrix. So just get comfortable with seeing some things like Y matrix. Okay. The way you use it is actually not very hard, right? This basically gives us a matrix version of Ohm's law. Okay. YV equals to I. This is our matrix version of Ohm's law. And we'll be building up on this equations, okay, to basically we'll try to get to power. Right? We'll try to get to power. Here we have voltage and current. So if you look at the structure, right? So you have the structure. So there is a specialized. So sorry, actually, let's do this way. So most of the network we have, and we will see, is AC networks. This means our impedance is a complex value. Okay? For example, AC networks, anytime you have a resistor in parallel with an inductor and so on, this will be AC network, right? Because impedance has an imaginary part to it. Admittance will have an imaginary part. So Y is our complex. And so all the algebra we do will be complex algebra. But from a computer's point of view, it's not any harder. Right? It's not harder to do. Okay. So if you're using a computer to invert matrices, inverting a real matrix is as same amount of work as inverting a complex value matrix. Okay. So all these are so nothing really changes much associated with complex matrix. So again, most of our networks will be AC networks. There's one special class of networks called DC networks. Okay, it's called DC networks. DC networks are basically networks where all the lines are resistance. Right? There's no inductance associated with the line. So this is called DC because the inductance or capacitance doesn't enter into the picture. In that case, the Y will be a real matrix. Okay, all the elements will be real numbers. So can you guys think of a case where we use DC networks? Can you think of a system where we actually use sort of this direct current network? When we don't use any. Sorry, go ahead.
Oh, the airplane.
Yes, so this is using airplane. Yes, so this is airplane. You have batteries, you have sometimes, so this is sometimes. If your generator, so airplanes, you have generators that are AC, but sometimes you convert to DC to have internal DC network. Sometimes you have AC network. For example, if you look at a very large ship, an aircraft carrier, will still be AC network. You still, you have enough synchronous generators, it's easier to work with AC than DC. So sometimes in aircraft, you will see all DC. There'll be nothing spinning. And so that's one scenario. I think something else that uses all DC.
Vehicles.
Vehicles depend on the drivetrain. Depend on the drivetrain. So, right. So airplane vehicles all sometimes may use AC or DC depending on, or submarines, depending on the exact setup they want. So sometimes you see a mixture of AC or DC. Another case, you'll see DC as data centers. Okay. But now there's more and more data centers are trending towards full DC. Right? There's no particular reason within a data center to have AC networks. So a lot of data centers are going to all DC design, where you do one conversion going from the grid to the front end of the data center, and everything after is all DC. And right, so the chat says solar. Sometimes when you have a microgrid where the generation is mostly solar and batteries, it makes sense to do DC. Okay, so although still most of the grid is AC, you see more and more DC grids popping up, and this does make a difference when you solve optimization problems. So sometimes you'll see one technique especially designed for a DC network, but in this class, for us, we'll focus mostly on AC networks. We'll just focus on AC networks. Okay, any questions about DC or AC? Okay. Okay, so basically, when we have a Y matrix, right? So the way Y matrix gets used in practice is whenever you construct a network, you build this Y matrix. And since all this networking practice is added to, you do maintenance, you add lines, you do this kind of things, year in, year out. So we're often modifying the Y matrix, right? So sometimes we collect a line between two buses. Sometimes we disconnect a line. Sometimes we add a transformer. Sometimes, we add a source. We do all those kind of things. So, but if we use Y matrix, then doing all these things is particularly easy, right? So if you connect a line, for example, between I and J, you have a new line, has some impedance, right? And the admittance is 1 over Z. Then changing the Y matrix is pretty easy. You basically go to the original value, whatever was before, subtract Y out of it if it's for the off diagonal. For the diagonal, you add Y. Okay, so modifying the Y matrix is quite easy, quite simple. You don't need to rebuild the matrix from the start. Okay, there's no need to rebuild matrices from the start. Whenever you add an element, you can simply do modification to a few elements in the Y matrix. It turns out this is not the case we're using impedance, actually. Right, this would not be the case we're using impedance. So that's again the reason why we use Y matrix instead of Z matrix. Okay, all this sort of modifications are easy to do. Right, so removing a line is, yeah, go ahead.
So Yij, it's implied to be negative, right? So it's technically negative impedance minus another impedance, correct?
No, so this Yij is Ij's elements of your old Y matrix, right? So this Ij element.
And that was assumed to be negative, right? Because all the off-diagonal terms are negative.
Yes, but when I say Yij, it's already includes the sign inside of it, right? It's an element of the old Y matrix. That's why when we add a line, we're going to subtract Y.
Okay, makes sense. Makes sense.
Yeah. So this was the old element of the matrix, right? So the small y, lowercase y, is the admittance of the new line. So when we add a line, we subtract Y out of it. When we remove a line, we add y. We do the exact opposite operation. Okay, so again, it's a simple operation to add a line. When we add a source, we basically change the diagonal elements, and we add a current to the current source. Okay, so all these are easy operations. All these are easy operations we can do. Okay, so if you see a problem saying we have a network, compute y, now we add a line between, let's say, buses 1 and 3, compute the new y. It means you don't have to start from the scratch, right? You can just modify your own matrix. So last few comments about the Y-bus matrix. So if you look at the matrix, if you think of a power network, right? So let's say you have a power network. You have n buses. You have n buses. What is the most number of lines you could have? What is the maximum number of lines you could have? Let's say you have a network with n nodes or n buses. What is the largest possible number of lines you could have? Ideas? So let's say I have a graph, right, or a network with n buses. I'm going to connect lines. What is the maximum number of lines I can have?
Is it n-1?
It's not n-1, right? So n-1 is the minimum number of lines I need to connect the network. Right, so now I want to know the maximum. Maximum is definitely not n factorial.
N factorial.
It's not n factorial. It's not n factorial. That's not how this works, right? So basically, what is the maximum number? The max number of lines is n choose 2, right? You pick any two pair of buses, any distinct pair of any two distinct buses, that's a pair. You can put a line on them, right? So this is n choose 2 number of lines. Okay, so n choose 2 is roughly order of n squared. Okay, so roughly order n squared. Right? So let's say you have 100 buses. Roughly on the maximum number of lines you can have is roughly 10,000 lines, 100 squared. Okay? For a power system, do you think we get close to this number? Do you think we get close to n squared? Right? Definitely not. Okay, we're very far away from n squared. So for a power system, we are roughly order n. Okay, so this is what sparse network means. So some of you may hear the word sparse network, or the power system is sparse system. What this means is the number of lines scale with the number of nodes, and then not number of nodes squared. Okay? So a power system, what we see, this is actually a quite mild scaling factor. So this is like 2 or 2, mostly 2n or 3n, sometimes even lower. Okay? Sometimes even lower. All right, so it's a quite sparse network, right? So the minimum number of lines you need is a -1. That's a tree. It's not much more denser than a tree. Okay, so it's quite a sparse network. So this, for example, here we'll give an example, right? So if you look at a system, this is for actual system, there's 1,500 buses. You really don't have that many lines. Okay, so most of things are 0 in our Y matrix. Okay, so for example, here it says 99.7% of the elements in the Y matrix are 0. And in practice, you do see this kind of number. So 99% of values are actually 0. Again, a sparse matrix means that most values are 0 in this matrix. Okay. So when we store a sparse matrix, when a computer stores sparse matrix, the way it stores it, it doesn't store the zeros, right? It doesn't think of 0 as just a float, just as a normal floating number, right? It's not a normal float. What it stores as only stores the non-zero elements, and basically the storage need for storing this Y-bus matrix is quite low. So if you want to store a matrix naively, you want to store a 10,000 by 10,000 matrix naively in your computer, you may run out of memory. Right? The matrix may be too large to be stored. But because this matrix is so sparse, storing all these matrices are sort of trivial to us. Okay? So the network, although it's very large, it is quite sparse. There's mostly zeros in the Y matrix. Most nodes are not connected by lines. Okay? So it's a system with many nodes, many lines, but far away from sort of n squared number of lines. Any questions about this? Right, so most data can be stored pretty easily. So a interesting side note with the power system. So if you have heard the word planar graph before, it's interesting to know that the US system is actually not a planar graph. There are lines at the same voltage level that crosses each other. So that's an interesting side note. It's don't know why the system is designed that way, but turns out it's a sparse network, but not a planar network. Right, so because it's so sparse, when you solve this kind of matrices, we'll never do Y inverse. Okay, so it's never us. Okay, you never compute V as Y inverse times I. This is not computed. Okay, we're never computing the actual. When you work with this in practice, you never type in inverse of Y. It's just not how it works when you have a sparse matrix. Rather, there's a lot of special ways to solve a matrix when this is all sparse, when this is mostly zero in this Y matrix. There are special ways you can solve it. And all software, all power system analysis software handles this. Will have its own special ways of handling the sparsity. For us, you don't need to worry too much about how sparsity is handled. In more advanced graduate classes, we'll think more about sparsity and algorithm and things like this. But for you, sort of the what you need to know is that in practice, you don't type in inverse of Y. But for homework questions and the exam, because all the matrices you'll be looking at are small enough, you can just compute Y inverse and multiply by I if you need to compute that. Okay, but it's keeping in mind in practice, it's not solved as computing the inverse. Okay, you never solve a linear equation by computing the inverse. Okay, this is never done. What you do is there are special techniques to do this. Basically, you can think of as a multiplication of the Gaussian elimination. Okay, there's ways to do Gaussian elimination very efficiently to solve this in practice. But in homework-wise, homework exams, it suffices if you want to do Y inverse. Small enough, you can do Y inverse. Any questions about dealing with Y matrix and solving linear equations?
I had a question.
Yeah,
how do you determining whether one is matrix is sparse or not?
Okay, so you compute the number of zeros. So there's no clear-cut rule for this, but the rule of thumb is you compute the number of non-zero elements in the matrix. If it's much less than n squared, right? So there's n squared elements in this matrix. So it's much less than n squared. It's a sparse matrix. So roughly, the rule of thumb you can think of, if let's say 80% of the elements in a matrix are zero, we'll call it sparse matrix. So what boils down is when you do programming in sparse matrices, all this is stored as a linked list, and that gives you a very easy way of solving equations. So sparsity does matter, right? None of our power system tools work if we don't use sparsity. But that, in some sense, is a solved problem. We're very good at using sparsity. So unless you're dealing with the core software, you are most time not aware of sparsity being used. Okay. All right. So this is all we'll say about the linear equation. Basically, given V, I or V, find each other, right? So given voltage or current, find the other one. That's really by a linear equation. And the linear equations in this class, keep in your mind is we're good at solving linear equations, and the only thing we're good at is solving linear equations. Okay, so that's a thing to keep in mind. We're gonna use basically whenever we get to a linear system of equations, we're gonna declare victory because that's what we can do. Anytime it's nonlinear, we don't know how to solve it. Okay, so when we get to nonlinear equations, our entire method will be approximating with linear equations. Okay, so our building block for the rest of the class is we can solve linear equations. Okay, so when we will get to nonlinear equations, maybe on Wednesday, and our goal will be repeatedly using linear equations to approximate. Okay, so really, we're going to use this as a building block, and we're going to assume this is an easy problem, or somebody has solved this problem for us. Okay, right? So the reason we need the nonlinear equations, we'll now look at power flow problem. Okay, this is sort of the fundamental problem in power system operations, solving the power flow problem and the optimal power flow problem. Okay, and this is a fundamental problem and still not a trivial problem. It's because in practice, we don't have current sources or loads that are constant current load. We just don't have this type of load. Right? As we said last class, most loads we have are constant power loads, not constant current or constant voltage or constant impedance. Okay? Your computer is a constant power load. Your computer doesn't care basically what voltage it's operating at, or the adapter doesn't care what voltage it's operating at. It will pull the same amount of power. And most electronic loads are constant power. Okay? So actually, the only thing in your home that may be constant impedance is maybe your light bulb and your stove, using an electric stove. Those two are maybe the only constant impedance things you have. Everything else is constant power or a mixture of constant power and constant impedance. Okay? So yeah, so that's basically the loads we have. Okay? So we don't have constant current loads. We don't have constant impedances. That's why the equation, so in practice, so the equation what we had is yv equals I. We don't solve this very much. Okay? We don't have constant I loads. We don't have this constant current loads. What we have is constant power. Okay? What we have is we have constant power. So if you have a network, okay, so let's say these are your load. Constant power, so constant power means some PL, QL, PL, QL, this are constant power loads. And then we have generators. This is my big Y matrix, okay? So power flow means that, so if you look at this system, right? We know the load in the system. So we always know what the load wants to draw. Okay, so the goal in a power system is never figure out what the load is, at least for this class, because we're always given the load. Right? Your computer wants to draw 100 watts, draws 100 watts. So the goal of solving power flow equation is to say, most time, given load, find V and theta. Okay, so our goal is to say, given P, let's say given P and Q, want to find V and theta, the voltage and the angle of the system. So why do we want to find V and theta? Right, so the system is operating, we have no control on the load. Right, so the system operator most times have no direct control on the load. So the load is changing however they want to change. But then why do I want to find V and theta? Why do I care about V and theta?
Because they affect the current.
But why do I want the current? Right? Why do I care about the current?
I guess thermal losses and stuff like that, or do you want to limit how much current there is, or how much is being wasted if it's like lots of reactive power being used up.
Right, so it's close to what we want V and theta. So remember, for this case, we have no control of the system, right? The V and theta are determined by the loads. So the reason we want to find it is not yet to do control. Okay? We don't control the load. So we cannot arbitrarily change V and theta. We just want to find out their value. The reason we want to find out their value is the following, right? So we have buses. So we have, what we have is we have limits on V, on the magnitude of the voltage, right? We have transformers, we have generators. They're all designed to operate at a specific voltage level. So we want to solve for V to check we're safe or not. Right? Are we in the safety region or not? Are we violating any voltage constraints? Similarly, we have limits on line flows. Okay, we have limits on line flows, right? We have the thermal limit, we have stability limit, and this can be determined if we know V and theta. Right? So we want to figure out from the load, we want to figure out V and theta, because V and theta can determine other variables in the system, and we have constraints on other variables in the system. Okay, so this is very much a checking procedure. We're checking if we're operating safely or not. Okay, we're checking whether we're safe or not. Okay. So we're no longer finding, IMVE. So our goal is we're given active reactive power, not currents. We want to find V and theta. We want to do this. So we're finding V and theta because we can think of V and theta. This is state of the system. So from V and theta, we can compute everything else. Other values, right? If we know V and theta, we can compute things like line flow, we can compute the currents, we can compute all those things. But in practice, since we're never, right? So these are the things we want to check, whether things are safe or not, But since we cannot compute this, since we cannot directly measure the theta and V, we need to compute it from P and Q. Okay, so we need to solve for V. The powers. Okay. So the real important thing is solve for V from the powers. Okay. All right. So any questions about this, right? So it's important to remember why we're computing V and theta. Okay, right now we're still not doing control yet. We want to check for things like stability limits. And the stability limits in a transmission line, we cannot directly check. Right? We cannot directly check whether they're satisfied or not from the end loads. Right? So if you say, our campus is consuming 50 megawatts, that doesn't tell me whether the current flowing on the line to our campus is safe or not. Is it violating some constraint or not, right? So really, we have to take the loads, compute the voltage and current, compute the voltage and angle, and then check whether we're operating safely or not. All right, so okay, so again, so it's useful thing to remind ourselves is, why can we not directly measure V and theta? Right? Why go through this computation? Why not just buy sensors to measure V and theta? I mean, it's load dependent, right? So we can do the calculation precisely because they depend on the load. But it's easier to directly measure the current, right? We have sensors. Right? So everything, of course, is consistent because they're relating by these equations. But why not just buy sensors, put a sensor on every bus, and just measure V and theta instead of doing this computation? What's difficult about directly measuring all these numbers? Okay, so if I ask you to go to a transmission line, go to a pole and say, okay, go measure the voltage, how will you do it? Physically, right? So I point you to a transmission line at some pole and say, okay, go measure the voltage for me. Right? So one is measuring voltage is not all that simple. Okay, I need some transformer to measure voltage. And when the lines, 20 meters high, there's high voltage, there's high amount of power flowing out. This is not easy thing to measure. And measuring angle is even harder. Measuring angle is even harder. Because to measure angle, what you need is you basically need to measure the time domain current flow to measure angle. And this requires you to build a current transformer. And building a current transformer for high voltage and high current systems is very challenging. It's quite challenging to build accurate sensors when everything's, when the voltage is high, when the current is high, when the power being transferred is high. Okay, so if we could directly build sensors, we would, right? It'd be easier, at least to get more information about the system. We'll just build more sensors. But it turns out it's difficult to construct good sensors. And this is pretty expensive to deploy them all through the network. Okay, so right now, still the way to say measuring power is easy. Okay, we're very good at measuring power. We're not very good at measuring voltage. Measuring angle is even harder. So let's just get the loads and compute the voltage and the angle. Then compute other things of interest in the system. Okay, so we'll get the measurements and compute the computation. So if you guys take power electronics classes, you may get to a point where you do designing these measurement devices. Like how do you measure current in a transmission line? Is quite interesting. Actually, there's a lot of interesting engineering goes into measuring current. In this class, we'll assume that we just have power, and then we'll compute everything else. Okay, we'll through computation, we'll figure out other things. Okay. All right, so again, the problem definition of load is power consumed. Okay, generators, again, the thing to remember is it is not a voltage or current source. Okay, our generators are not ideal voltage sources, are not ideal current sources. Okay, this is not how our generator work. Okay, our generators convert one source of power to electric power. So it's limited by the active power and the terminal voltage. So when you view a generator, if you want to think of generator as a black box, what the generator does is the following. Generator is some black box. Okay, this is our generator. That fixes as a fixed voltage okay, so this is really our black box model of a generator. Okay, it's outputting some active power, right? Some active power at a fixed voltage. Okay, so it's neither a ideal voltage or current source. It's basically ideal power source that operates at a fixed voltage. All right, so this is our model. So basically you have loads and generators. And when we put these things together, what we'll have is we'll basically solve for the nodal voltages, right? So we'll solve for this is complex number. Right, so this is both V and theta. So we'll solve for the complex nodal voltages when we write down all those equations together. Right? So any questions about this? Okay, so let's take the break now, actually, because we're getting into a lot of equations afterwards. So let's take the break now. Let's come back at 10:28, and we'll start write down this nonlinear equations. We'll write down the power flow equations along a branch, then in the entire system. Have an idea of the types of equation we want to solve in this class. So let's break now and come back at 10:28.
Professor, I had a question.
Sure.
So for your 451 or 551 class next
Yeah.
quarter, I was interested in taking that, and I just kind of wanted to know a little bit more other than what's posted online,
Right.
just for the description.
Mhm.
I was mainly curious about like kind of workload compared to maybe this class, and just what specifically is going to be divulged.
Mhm. Right, so the workload will be a bit lighter than this class. So not as much as sort of calculation as this. I guess not much as, solving matrix equations or doing programming. So this class, as we go on, will trend more into programming because we need computers to solve all these type of problems. In the 451 class, we won't have this. So it'll be still mostly a one generator connect to grid. This kind of one generator connect to grid, not so much a system. And the class is divided into two parts. One is the physical and mechanical and electrical setup of this generator. So basically, we'll cover, how do you make a wind power generator? So there's induction machines and synchronous machines. We'll look at the protection issue around with it. Basically, what happens when wind change, right? How do you do protection? How do you design power electronics around it? How do you, synchronize this machine with the grid? So that's one half of the course. We'll look at this. So basically, it's a mixture of electric machines with power electronics connecting the grid. Another part of the course, we'll think about the system integration issues. We'll look at things like, thinking about the randomness, right? So we'll cover basic probability, so very basic probability, but give us a way of thinking probabilistically about all these systems. We'll look at how storage works together with wind. So that'll be something new for the next quarter. Before, we really haven't covered storage, but we want to cover it this time. Think about how storage works, right? When things are uncertain, if you have storage, which is a buffer, how do you value storage? How do you do calculations? We'll talk a little bit about markets, right? Because interesting, or if you have let's say natural gas plant, there's a obvious cost curve. It's the price of gas times the efficiency gives me the cost of electricity. For wind, there's not really that. So we'll think about all this kind of questions. But in terms of style, be more single machine to grid, not so much a very large system.
Okay. And then what's the difference between 451 and 551?
There's not in the lecture, so it's cross-listed between undergrad and grad student. So you can take it as a grad credit if you need to.
Okay.
So what happens for all these classes is the grad student will be asked to do a project, the undergrad student will not do a project.
So I want to sign up for 451.
Yeah, so you can sign up for 451 if all you need is undergrad class. If you need a graduate level class, so I say you're taking a master or PhD, you need a 500 level class. It counts as a 500 level class. So
okay. All right, sweet. I'll probably see you there then.
All right, thanks.
Thank you, Professor.
Hey, Professor, I've got a quick question. Can you go over again how you got the max number of lines?
The max number of lines. Okay, yeah, let's go over that. So let's say. Right, so let's say max number of lines, right? So let's say if I have 3, right?
Mm-hmm.
So the number of lines I have is any of them can connect to each other. Right, so this is for 3, this is what I have. So any pair can have a line. right? So this is the sort of the max number of lines. Similarly, when you have 4, for example, this is a possible system. It definitely doesn't have the max number of lines, but has,
Sure.
lines that makes a connect system. When you want the max number of lines, you basically say, this 2 bus can be connected, this 2 bus can be connected. Right, so this is so we're basically choosing any pair of nodes and putting a line between them. Right, and they won't do the calculation as you have n nodes, right? Each of them has n minus 1 neighbors. So there's n times n minus 1. Right, so this is the number, this is a order pair we have. But if you look at this, let's say number this 1, 2, 3, 4. 1 to 2 and 2 to 1 are the same. Right, so we're double counting lines like this. So then we divide by 2 to take care of the double counting.
Yeah, that makes sense. Okay.
So this is precisely n choose 2.
And choose 2. Yeah, that makes sense. Thank you.
Professor, I had a question. Is there any courses that teach more in depth about microgrids?
No, unfortunately, no, we don't have any teachings on this or microgrids.
Okay, just checking.
The closest you will have is a distribution system class, but not precise on microgrid. Now, microgrid is a new enough topic that yeah, we don't have a course on that. So as a sort of broader topic, if you guys are interested, so we're thinking about redesigning the power and energy curriculum, both at the undergrad and grad level. For things, for example, put things courses like at times more to do with microgrid or have more integration between power electronics and power system analysis. We're thinking about designing courses and maybe removing some of the old courses that's not very popular. So you have suggestions, let me or Professor Daniel Christian know. Yeah, we'll try. So you'll start to seeing sort of the redesign of curriculum. Maybe not this year, but starting from next year.
Okay, thank you.
Thanks. Right, yeah, so census cracking chat. So Professor Daniel Christian is working on a microgrid project. And if you want to know more, you can talk to him. And we have a grad student who's working on this. So if you are interested in microgrid and you want to do some research, you have time to do some research, you can get in touch with him. And I know they're looking for people to work on this. There's the actual microgrid, so I think with Snohomish PUD. So maybe something good project to work on, right? You get to see the actual grid and you get into a lot more details. So it's a nice project. All right, okay, so let's look at some equations. So when we look at equations, what we'll do, we'll often do is we'll think of some generic bus K. Okay, so bus K just means some generic bus in the system that we have. So how do we model a generic bus, right? So the way we draw a bus in this kind of diagrams, our bus will be this kind of bar. Okay, so this is our bus. Okay, so this is bus K. And what we have on this bus is the following thing. Okay, so so to connect to this bus, what we have is, we can think of, we have a generator and a load. Okay, connect to the bus. So all these values can be 0, right? So the generator, if we have the generator value being 0, it's as if there's no generator. But generically, I think of there's a generator and the load connect to the bus. So the generator is generating some active and the reactive power. The load is drawing some active and reactive power. Okay, so this is what we have on this. And then what we have on this thing, so the net amount of generation minus load gets injected to the bus. So this is written as PK injected and QK injected. So this is injected to the bus and flows to the rest of the network. So where does this power go? Well, so we can assume this bus is connected to some other buses in the system. So let's say it's connected to, draw this more straight. Bus I, and let's say here is connected to bus J. Okay, so this power that's injected from this bus gets to be disconnected. Gets to be distributed to PKI, QKI, flowing from K to I, and this is PKJ, QKJ. Okay, so this is our generic model of a bus in the system. Right, so this is how we would think of the bus in the system.
Professor?
Yeah, go ahead.
Is the PKJ equal to the PK injection?
No.
Because I feel like the generator has to be injected to the bus K first, then come back to the bus load, to the load.
No. So in this model, the way we're going to think about it, we're going to think of the load will consume the generation, if there are generation, and then the net of generation minus load is injected to the rest of the network. This is our internal model. This is our internal model to a bus.
If the load is consuming more than the generator is producing, do you have a negative injection?
Right. Yeah. So all numbers here can be negative. Okay. Every number here can be negative. Maybe except the generation from the generator, but you can think of every number can be negative, right? So when we draw this, we say 2 bus I. It could be a negative number, meaning the power could be flowing from I to K. Okay. So all of this can be negative. Right, so injection, if positive, means we're putting net power into the grid. If it's negative, meaning we're withdrawing power from the grid. So that's fine, right? We'll allow both positive and negative numbers. Okay, we'll allow both of these. Right, so this is a good question, something to keep in mind. Right, so injected power doesn't mean as positive net power into the network. It's a variable term. That means the net power I have at this bus could be negative if I'm a low bus. Okay. Yeah, good question. Yeah, so these are good questions, right? So if you have a question, please ask. This is again a fundamental building block of the system we'll have. Yeah. So yeah, so if you say my handwriting is hard to read, then there's a sort of a computer draw diagram in the notes, right? So again, the thing to remember is all those numbers could be negative, right? To bus I could be a negative power flowing to bus I. Right? So power injection could be positive or negative. So any question about this terminology, the convention we have? Okay, so this is our terminology. And we're going to build, or basically we'll write equations for all these numbers, for all these variables. Okay, so next step is starting to write equations for these. So let's write some equations, right? Let's write some equations. So let's write the power balance equation. Okay, let's write the power balance equation. So to write the power balance equation, let's write it following ways, right? So as commented before, right? So the power injected has to be equal to the generation minus load at this bus. Okay, so we're going to think of this as the net at this bus. Similarly, this is QG minus QK. Okay, so these are the net injections. So this is one equation we have. Then we can think about the power balance, right? So this is our bus. We're injecting some P and Q. And my power is flowing out. Right? So my power is flowing out somewhere. So we must have a power balance between the power I inject to the bus and the power that flows out from this bus. Okay, this is what we always have, right? Power must be balanced in this situation. So remember, the bus itself is some, this fictitious thing we're imagining to be a one-pointed network, right? So this bus, everything comes in, must go out. Okay, this bus bar itself doesn't consume any power. Okay, so that's what the power balance we have. So this means that the power injected must equal to power flowing out. Okay, so this is the power balance we have. So keep in mind that this can be negative. But negative or positive, this balance must hold. Okay, this power balance must hold. Okay, so this is how we relate what happens to one bus to the rest of the network, right? So they're related by this power balance equation. And so from this power balance equation, so I need a shorthand to write all the buses connected to this bus. Okay, I need a shorthand to write all the buses connected to K. I don't want to write this out every time. So we use a notation. NK is a set of nodes or set of buses connected to K. Okay, so you have some bus K, some node K. Let's connect some other bus. We'll connect them. We'll basically think of them together as a set called NK. Okay, so all nodes connected to K. Okay. Now our equation becomes, we have the injected power equal to the net power balance at this bus equal to all the outflow from this bus, right? So the way to read this equation is this power injection is equal to the power flowing from out of bus K to all its neighbors, okay? Some PKI. This is the way to read the power injection. And then similarly, we have the same thing for the L equals to the net net outflow of all the reactor powers on each of the branches connect to bus K. So this is our power flow. This is the power balance equation, right? So we have the net injection equal to the total, the net outflow from the bus. Okay. Any questions about this?
So we're calling the outflow as positive.
So the convention of as this number is positive is flowing from K to I. If it's negative, it's flowing from I to K. Yeah, that's the convention. Yeah. But it doesn't mean it has to be positive. All this can be negative. Okay. Any other questions about the convention we use here? Okay, so this is our power balance equation. So this is one of the equations that couples all the buses together in the network. Right, so this is a coupling equation. So again, this is all the things typed out here. Right, so you can, yeah, so this is a typed out version of all those, of the equations. Okay. So now we have to relate power to voltage. Right, so remember the goal of solving powerful equations is given power, find voltage. So let's relate this to voltage. Okay, let's relate this to voltage. So relating power to voltage, right? So remember what we have. So this is again our bus. This is our bus. What we have is we have, let's say some VK. Let's say some VK. So we write a bar to explicitly denote this is a complex number. So we have some complex voltage at this bus. Then let's say I have some current. Okay, so this is IK injected. This is the current I inject. This current I inject into the bus. So what does this current injection equal to? Okay, let's think about what does this current injection equal to. Then this current injection equal to, right? So similar to power, this current must equal to the net outflow. This current must equal to the net outflow, right, of other things. So this is the, as we can think of this as the current, or let's write this, IKI. Okay, so this is the current to bus I, right? This is current to bus I. Okay, so this is the what we have. So let's think of the injection. Okay, let's think about the injection. Okay, so we have, so how do I relate this injection to the voltages in the network? How do I relate this?
Power divided by voltage?
So we don't know the power, right? So it'd be nice to, because our goal is to use this, right? So our goal is to relate power to voltage, right? So we need basically what equation we have, the fundamental equation we have, that fundamental equation we have is, we know that S, we know this thing injected as P injected plus JQ injected. Okay, we know this, right? We know P times Q equal to VK, sorry, VK IK injected whole thing complex conjugated, right? We know this whole thing, we know this equation is true. But this is the current, right? So what we want to do is we want to write power just a function of voltage and not as a function of voltage and current. This is our goal, right? So we want to write just as a function of voltage because current and voltage depend on each other. Current and voltage depend on each other. So we don't want it as both voltage and current. So how do we eliminate current out of this equation and just have voltage? So our goal, remember, our goal is to go from given S from V. Okay, so we have some equation that has S on one side, V on the other side. Potentially we can solve that equation for V. Okay, but right now our power equation has S on one side, voltage and current on the other side. So that's nice ideal. Right? So ideally, I just want voltage on one side. So I can solve for the voltage. So how do I convert I to V? How do I relate I to V? And you remember the first part of the lecture, right? So use a admittance matrix, right? Use Y, right? So that's Y. That's the reason the Y matrix is important. Because I know that the current injected is Y times V. Okay? This is our basic relationship. So IK, this is just the case element of the entire current vector. Okay, this is just the case element of the entire current vector. So what we can do is we just read out one element of this matrix vector multiplication. So if you read it out this way, what we have is this is basically you fix the row in the matrix and you sum over the columns. Ki times Vi. Okay, so this is what the I equals Y times V matrix tell us. Right, so this is what we know from our matrix. All right, so this is what we know from that. So what allows us to do is we can substitute just using V. Okay, so instead of power equals to voltage times current conjugate, what we want to do is we just want power equals to a function of the voltage. And we can do that because we can write an equation that relates current to voltage. Okay. So we substitute more. What we have is we have Vk times Ik injected star conjugate. So this is Vk sum I equals to 1 to n Yki Vi conjugate. So we can write this in as sum of I equals to n Yki conjugate Vk Vi conjugate. Okay. So this is how we relate power on one side to voltage on the other side. Okay, so this is why power is a quadratic basic equation of voltage, right? So it's a complex multiplication of voltage variables to each other. Any question with this equation? Again, you'll see this equation quite a bit. Okay, so this is the basic equation we have. The power injection at a bus equal to a weighted sum of the product of the voltages, where the weight in the weighted sum is the admittance matrix, is the elements of the admittance matrix. Okay, so this is a sort of mechanic. This is the mechanics of this calculation, right? Okay, so are we clear with this equation? Okay, all right. So this is the equation we have, right? This is the basic equation we have. So let's write this again, Sk injected. Okay. So now the equation starts to take shape, right? Because remember, for power flow equations, solving power flow equations, solving power flow analysis, this is given. We are going to find the complex vectors V. Okay, so we're given one side of the equation, we're trying to find the other side of the equation. This equation easy to solve? Okay, do any of you know how to solve this kind of complex equations? Right, so the problem with this equation is basically it's not very easy to solve. This is a very compact way of writing power flow. right? Because it's just a summation of, a few terms. However, if I ask you to solve this equation, it's probably very difficult to think of how you even get started on solving this equation. Right? It has complex numbers in it. How do I, there's conjugating it. There's multiplication of complex voltages. So this will seem very difficult. So this is a compact version. We'll write if we want to save space. Okay, so you see, sometimes we write this, we want to save space. To get it to be more understandable, sort of develop some more intuition on this, be useful to write this in polar coordinates. So this is in rectangular coordinates. We can write this in polar coordinates to get a little bit more intuition and try to get into a form that we can think about how to solve it. Okay, so let's write this in polar form and think of how the equations work in polar form. Okay. So let's do a bit of complex algebra. It's not very hard, but we'll try to do this a little bit slowly, right? So we can get an idea of where the polar coordinates come from. So bipolar coordinate means we'll write things into magnitude and angle. Again, theta I, and the yki, this is gki plus jbki. Okay, so the polar actually means that we'll only write the voltages in polar coordinates. For emittance, we'll keep in rectangular coordinates. And the reason will become clear once we work through this. Okay, so the goal is, instead of writing voltage as a complex number that's in rectangular form, we'll write this thing as in polar form. So we start with our equation sk injected. Okay. This is, remember, x1 to n, y ki complex conjugate, vk, vi conjugate. So let's do the substitution. So if we do a conjugate of the y terms, right, we basically flip the sign on the imaginary part. We flip the sign. Vk theta k, vi minus theta I, right? So it's a conjugate. Again, we flip the sign on the angle for a polar coordinate. So if you have any questions along this, please say so, right? So this equation, again, when you practice, you should go through this calculation by yourself, right? So this is a lot of you see this polar equations a lot, and it comes from this calculation. So next step is we'll collect the magnitudes and the angles together, theta k minus theta I. Okay, we'll connect these angles together. And we use Euler's formula to write the angle, okay, to break up this angle. Vk, Vi. This is cosine theta k minus theta I plus j sine theta k minus theta I. Okay, using Euler's formula. And so now the rest is just multiplying out these terms and collect the real and the imaginary parts. Okay, so now there's no mystery. So there's no mystery to any of this. Now we're going to multiply out and collect parts. So we get one part. That's all real numbers. So this is gki cosine theta k minus theta I plus bki sine theta k minus theta I. So we get this term. For the active part, active power, plus j, we got a term for the reactive power, gki cosine theta k minus theta I minus okay. All right, so this is our polar form, basically. Instead of we'll write out voltage in terms of magnitude and angle. And we basically have some sinusoids that determines active and reactive power flow. Any question on this? On this? Okay, so the active reactive power flow. And this angles come out. Okay. So if you do a sanity check, let's think of does this make sense? Okay, so let's do a sanity check and see if this thing makes sense. Okay, so so we get this. Let's do a check. Let's suppose that, so for example, suppose all this. Okay, so suppose all the voltages are what? Okay, right, so we're using per unit anyway, so all the voltages are close to what? So let's assume they're all what? And they say angles are all the same. Okay, I say angles are the same, voltages are what? Do I have power flow in the system? Should I have power flow in the system? No. So from the equations, do we get this? So let's look at this. Okay, so let's look at this carefully. Right, so the idea is, if the voltages are all one, the angles are the same, means all the complex voltage numbers are all the same. Right, so power flow should be driven by a difference in voltage. If there's no difference in magnitude or angle, there should be no power flow. So this is a sanity check for us to do to make sure our equations are correct. Okay, so let's do the sanity check. In this case, let's say this SK. Okay, so the voltages are one, so let's not bother writing it. GKI. Then what's the cosine? What does the cosine term become? What does the cosine term look like? If all the angles are the same.
1.
1, right? Cosine terms are 1. What happens to the sine term? 0, right? All this cancels out, so good. J. Okay, so we have these two terms. This 0. Is this 0, right? We said if all the voltages are the same in magnitude and angle, that should have no power flow, right? But if I plug this into the equations, do I get 0? Is this correct? Okay, so this is what we get, right? By plugging into the equations. Seems a little bit mysterious. Not it. So the sine terms, good, all disappear, all completely gone. The cosine terms remain. Cosine of 0 is 1. Seems I still have some terms, no? So what's going on here? So what's going on, right? So the important thing to remember is think about this sum, right? Think about this sum. Okay, think about this sum. We were summing like this, right? So let's just look at this sum. Let's break into two parts. This is GKK plus sum I not equal to K to N, GKI. How are they related? Right, so one term is a negative of other terms, right? As a sum of negative of other terms. Remember how we construct the Y matrix. We construct the Y matrix. This is the negative right? This is our Y matrix construction. The diagonal is negative of the sum of all the off-diagonal terms. This is our construction. So this is actually 0. Okay, so it works out. It's actually 0. So all things checks out for this. Okay, so things are still consistent, right? So this is just some sanity check for us. Turns out we passed the sanity check. Okay, so the equations work out the way our intuition works out. Right, so it's good to do sanity check like this, right? So whenever you do a long derivation of equations, it's good to check these corner cases, right? To not make a mistake, right? And to check there. And again, so there's good reason why the matrix Y matrix constructed that way. Okay, if it's not constructed that way, this whole thing doesn't work. Right? So because the Y matrix is constructed that way, and we can, it turns out, all right, so the equation still makes sense. Okay? Any questions on this? Okay, so that's just good habit to get into, right? Whenever you do a long set of equations, check corner cases, right? So 99% of the time, if you have error, if you have a bug, you'll catch it by corner cases. Okay. So we passed this corner case, and this is just again a repeat of the algebra I wrote out. So when you collect them together, these are called the power flow equations. Right? So this is a very basic. These are sort of the basic equations we have, the fundamental equations we have. And what they do is they basically relate power and voltage. So they relate, to remember power, other things that physically what we determine in the network, the load powers. Physically we set these. Voltage are the state of the system, right? Once we know voltage, we can compute everything. So power flow equations relates physically what's going on. We have constant power loads. Generators have constant power, active power. Voltage, and so by the equations, we want the variables that allows us to compute everything are V and theta. So this relates the two to each other. Okay. And they're nonlinear. Okay, they're nonlinear. And there's a system of equations. Right, because this is for all k. For every bus in the system, I can write out this active and reactive balance equations. So there's a system of these. So I have a system of nonlinear equations. Okay, and basically when I say solve the power flow equations, you solve the system of equations. Right?
Professor?
Yeah, go ahead.
So for this equation, the QK injection is VK times VI times GKI is the sine theta, not theta.
Oh, did I copy it wrong?
That's in your one is the
okay, yeah,
cosine.
so then I should be sine. So go as we typed out.
The sine and cosine.
Sine,
So
cosine.
how about the example here?
Yeah, so let's see how this example works out. Yeah, the example still works out, right? So this is B here, right? This is just B here. So the G terms work out this way. For this B term, we have the same thing. We have BKK is a negative of the sum of BKI. Sorry, BKK is the sum I not equals to K to N BKI. So it still works out. If you do this whole entire summation together, everything cancels. Okay. Right, so it works out. Yeah, so did I type this correct? Yeah, sine is correct, sine is correct. So yeah, good thing I typed this out. So yeah, so we're gonna go with, yeah, so it's cosine sine, sine cosine in this term. So I guess look at these two equations. This is the correct set of equations, and again repeated here. So these are the power flow equations.
Oh, how the BKI? Can I see the BKI?
See the BK? Okay, sure, go ahead.
So the BKK equals to negative BKI, and
yeah.
But how the JKI?
Same thing, right? So you can decompose the sum into the KK's term plus the other terms that's KI when I is not equal to K, right?
So we want
this sum decomposed in two parts.
So we want the JKI minus BKI equal to 0?
No. They're both individually 0. Right? So this term is 0.
Oh,
because
individually
this
zero.
j cancels out. This term is 0 because it cancels out, right? So for a complex number to be 0, the real and imaginary parts are both 0. That's what 0 means here.
Nice, thank you.
Yeah. Okay, good. Other questions about the power flow equations? The power flow equations? Okay, so these are power flow equations. We'll get to how to solve them next class. We'll get to how to solve them next class. And the takeaway is, even though they look complicated now, well, algorithm we'll use to solve them is not very hard. It's not very complicated. Okay, it's not terribly difficult to solve this equation. The only tricky thing being, we'll present an algorithm to you. We'll look at an algorithm. That algorithm works like 95% of the time. To get it to work for the rest of the other cases is much more difficult. But if you look at these equations and it seems complicated, that you've never seen nonlinear equations before, you don't know how to solve them, don't worry too much. There is a simple algorithm that you can write to solve these. Okay, there's a good simple algorithm that we can have. We use to solve these. And basically, it's based on successfully approximating these equations as linear equations and solving linear equations one at a time. Okay. So it's not very difficult to solve these for most of the times. All right, so this is still somewhat active area of research. We still look at how to solve these problems. We still look at how to solve this problem in research, because again, there's a lot of corner cases that makes life difficult. But we'll cover that next lecture. We'll start with the algorithm how to solve these. It's called the Newton-Raphson algorithm, and it's actually not very complicated. It's as simple as it's sort of how you would think of solving this problem. Right, so again, when we solve the problem, we're going to believe that we can solve linear system equations easily. And the only thing we know is, again, how to solve linear system equations. And then what Newton-Raphson is basically developed based on these assumptions. Okay, successfully refining these equations into linear equations and solving them. Okay. We'll start that next class. For the rest of this class, we'll go into a little bit more detail of how to formulate these power flow equations. Okay, so, but before doing that for the next 15 minutes, any more questions on these power flow equations? All right, so let's go look at a little bit of these coefficients in the power flow equations, right? So as a reminder, our line in impedance form is Z equals to R plus XJ, right? So when you talk about Y, lowercase y, it's just 1 over Z. So this is Rij minus Jxij. This is our easy term. Okay, so if you look at the capital Yij of the Y bus matrix, the ijth element of the Y bus matrix, that's equal to minus Yij. If I is not equal to J, Yii is summation of the lowercase Yij. So this is how we construct the Y bus matrix, right? And we have, remember Yij equals to Gij plus J. Just a review of terminology, a review of the notation we have in this. Okay, and then if you look at the physical meaning again of this equation, is again on the left-hand side, what we have is a net power injecting to the bus. On the right-hand side is the power flowing out of the bus, right? And the power balance means that they must equal to each other. Okay, so this is the idea we have. So if you look at, so there are sometimes, so all this depends on the angle difference. So sometimes we're lazy, we'll just write this angle difference. Okay, this you see theta ki, it's just theta k minus theta I. It's a way we're lazy of writing out the angle difference every time. So we'll just skip that. We'll just skip writing out the difference and use theta ki to denote the angle difference. All right, so okay, so all this is easy. So let's do an example. The reason I want to do the example is we need to figure out how many variables are there and how many of them can be set independently. Okay, so we can do this through a 2-bus example. So let's say this is bus 1, this is bus 2. Okay, and they're connected by a transmission line. Okay. So we have V1 theta 1, V2 theta 2. Okay, we have, right? So these are the voltages describing the system. Okay. So now let's look at the degree of freedom in this system. Okay, look at the degree of freedom in the system. What we mean by degree of freedom is how many variables, when we vary them, actually makes a difference. Okay, so the power flow S1, S2, or let's be more specific. Okay. P1, Q1, P2, Q2. Okay. So the degrees of freedom V1, V2. And the other degrees of freedom is actually theta 1 minus theta 2. Okay. So really, we can change the power by changing V1 magnitude, V2 magnitude, and angle difference between the buses. Okay, so remembering this kind of equation, so the important thing to remember is only the angle difference matters. The absolute angle does not matter on its own. We need to consider the angle difference. And so that's why we say the degree of freedom here, there is 3 degrees of freedom. Because we can have the angle, we can have the magnitude varying, and the angle difference here, and the angle difference here. Okay. So does this make sense? Does this make sense, right? So there's 3 degrees of freedom. So when we set, so for P and Q, okay, for P and Q, can I arbitrarily set P1, Q1, P2, Q2? Can I arbitrarily choose 4 numbers here? Right, so I have 3 degrees of freedom, meaning I can adjust V1, V2, and the difference in angles. So this means, normally what this means is, I cannot change, okay? I cannot change arbitrarily 4 powers all at the same time. I cannot change 4 things at the same time if I only have 3 degrees of freedom in this system. So I can only set, I can only set 3 of these. Okay, so I cannot change 4. Okay, I cannot change 4 variables independently. So for example, I can set V1, P1, Q1. This is okay. I can set, this is okay. I can say, I can specify these 3 numbers and ask you to find the rest. I can ask you to find the rest of the variables. Or, you know, you can do different things. You can do different things, right? So you can do for things like I can set, let's say V1, Q1, P2. This is okay. Okay, this is also okay. So what this means is I can only pick 3 of these as fixed quantities. As fixed, yeah, I can only pick 3 of these as fixed, okay? And the rest I have to get by solving, the equations by fixing 3 of the numbers. Okay, so this is the important thing to remember. When you give a system of equations, you need to make sure the degrees of freedom lines up with the number of equations you have. So for this system, what it means is I have 3 degrees of freedom. So I need 3 equations, 3 real equations to solve. Okay. Right. So for a larger system, there are 2n minus 1 n buses. There are 2n minus 1 degrees of freedom. So any thought on where I get this 2n minus 1 number from? Why are there 2n minus 1 degrees of freedom? Right, so what we have is V1, V2 up to Vn. And now these can be, these are variables, right? These can be set independently. I have theta 1, theta 2, theta n. Out of this n angles, there's n minus 1 degrees of freedom. Okay, so I have n degrees of freedom on the voltages, n minus 1 degrees freedom on angles, because again, angles, only the relative angle matter. So I can pick any of these angles to be 0, it doesn't matter. I only have the relative differences. So you knock out 1 degrees of freedom here. Okay, so only n minus 1 degrees freedom matters for the angles.
So are you always going to set one of the angles equal to 0?
Yeah, we're always going to set one angle to 0. It doesn't matter what it is. We'll just pick one and set to 0. So we're always going to set one angle to 0. So there's n voltages, so n degrees freedom on the voltages, n minus 1 degrees of freedom on the angles. Okay. And so we need basically 2n minus 1 equations to solve. Okay, right. So to solve power flow equations, when you look at in a system, how many equations do we need? I need 2n minus 1 equations because I have 2n minus 1 degrees of freedom. Okay, so if I can pick the right 2n minus 1 equations, then I can solve the system of nonlinear equations. Okay. Any questions on this? So we'll do this again. So next class, we'll do this with examples. But it's important to remember how to count the right number of equations. Because what goes wrong in practice most of the time is the number of unknowns and number of equations doesn't line up. Okay, so here I have 2n minus 1 unknowns, right? Or potential 2n minus 1 unknowns. I need 2n minus 1 equations. Okay, and the way we construct equations, as we'll look at this in detail next time, is we have different types of buses. Okay, we have buses, right? So remember, so 2n minus 1 means for n minus 1 of the buses, you can give 2 pieces of information. Okay, so for example, for PQ bus, we'll give the active and reactive power injection. So those are the 2 pieces of information I have. PV bus, these are the generators that give the active power and the voltage magnitude. So again, 2 pieces of information. Then to get the angle being 0, right, basically, I have a slack bus where I say the angle is 0 for a slack bus. So this will construct 2n minus 1 equations out this way, okay? So to get the sort of consistent set of nonlinear equations to solve. Right, so this is our equation constructing idea. So we'll do this in detail next week. Oh, sorry, not next week, on Wednesday. And we'll go into how do I solve these equations, right? So next time we'll look at how do we construct these equations and how to solve these equations. But again, the thing to remember is know how to do this kind of equation counting. Right? Any more questions on this part? Right, so if not, I'll see you on Wednesday. So as a reminder, we agree the midterm will be take home next Wednesday and Thursday. Right, so that's our midterm. All right, see you guys.
Thank you.
Thanks.
I have a quick question for the previous slide.
Yeah, go ahead.
Where we have the thetas right here. Yeah.
Yeah.
We have n-1 degrees of freedom for the thetas. Can we think of it another way that for the theta, we only care about the difference? So pretty much there's only n-1 differences. So you take theta 1 minus theta 2 minus theta 3. Is that the correct way of thinking, or is the correct way of thinking that we just set one of them to 0? So one of them is a theta?
Right, so yeah, so the more correct way, I guess, the sort of more fundamental way is to think of we only care about the differences. Right, so
Okay.
but operationally, that's the equivalent to fixing one of them to 0, right?
Okay. And my other question would be, I guess, if it depends on the differences. Well, technically, we can say theta 1 minus theta 2, right?
Mm-hmm.
And so if we say theta 2 minus theta 3, and we go all the way up to n, that is true that there are n-1 different equations. But then we could have also said theta 1 minus theta n, and then theta n minus theta 2. Yeah.
So yeah, I understand what you mean. So those doesn't matter, right? Because, for example, if you know theta 1 minus theta 2, and theta 2 minus theta 3, then theta 1 minus theta 3, it can be determined from these, right?
Oh, okay, true.
Basically, it's this thing. Right, so it's like this. Right, so it's you only need to know n-1 of the differences. Everything else is linearly dependent on that, can be determined exactly based on that.
Okay, makes sense. Thank you. Mm-hmm.